Over the last couple of years, we've built some new products that use these in the back end, and I thought I'd share it with you. So what are we doing today? 4 things. First thing is some motivation. So if you don't know what these data structures are, or have any idea at all, then I'll give you some motivation as to why you should care about them and why you might find them interesting. And then we're going to be looking at 3 probabilistic data structures, and I think that these are in order of complexity. We're going to start off with Bloom filters, which I think are quite simple to understand. Then we're going to go on to count, min, sketch, which is a little bit more tricky to understand. And then we're going to try our best to explain hyperlog-log, which is quite complicated. But first off, why should you care about probabilistic data structures? So I've tried to prepare some motivation for you here to see why you might be interested. Here are some storage technologies, and we have a line underneath these storage technologies. Now I'm going to put an arrowhead on this line and try and show you some things. So if we put an arrowhead on here, I'd say that the speed of these things, in terms of the speed of reading and the speed of writing, goes up as we go in that direction on the slide. So I think we all agree that memory is like the fastest thing to read and write to. Yeah? Some nodding. Good. Some people are awake. SSD, excuse me, SSD is, excuse me, wow, too much smoking. SSD is quite fast compared to hard drive, but hard drive is spinning disk, so it's slower, and tape is very, very, very slow. In terms of cost, as in actual dollars, pounds, euros, per 1 gigabyte of any of these things, you'll find that a gigabyte of memory costs you a lot more than a gigabyte of SSD, which costs you a lot more than a gigabyte of hard drive, and so on. So cost is an important factor. I'd also say that the ease of use to you as a developer is definitely in this direction as well. Because if you want to use memory in order to store data, it's actually really easy. You just initialize an array, or you initialize a set or something in your code. You use one line. However, if you're going to be using an SSD or a hard drive in order to be doing stuff with your data, you might need to use an open source framework in order to do it. So here's a very naive example of perhaps I could declare a set in memory of strings, but if that's too big for memory, then maybe I need to store some documents in Elasticsearch or maybe Solr. And if we're going further down the chain and we're using hard drives, we may need to use Hadoop or HDFS or something like that. The idea with this is that if we keep things in memory, it's so much easier for you when you're writing your programs to do stuff. The arrow goes in the other direction when we're talking about storage per node. So this is either on a physical server in your data center or an AWS instance or something. You'll find that usually you have more memory, less memory available than you do space on an SSD. And if you have some massive RAID configuration of hard drives, you can end up having a lot of storage available on hard drives. So the question is, how do we do more stuff here? Because not only is it faster, it's also easier to use in your code, and you have to spend less money on storing stuff, and you don't need to maintain any external storage systems. So that's the motivation for these data structures. So, probabilistic data structures allow you to do things in memory at a scale that you previously didn't think was possible. They often use a really tiny memory footprint. They also have really cool names. So when you talk to your colleagues about them and you show them your code or you submit your pull request, you look really clever, which is awesome. And I think they're really fascinating things. And as I said at the beginning of the talk, sometimes the barrier to entry is a little bit high. So what we're going to do today is we're not going to blind you with loads of mathematics. We're going to look at some Java code that does things in a naive way. We're going to look at the effect that that has on the heap and how much memory we're using. Then we're going to walk through the algorithm of each of these data structures and show you how they work visually. And then we're going to rewrite that code using the probabilistic data structure in the library that you can go away and use today. And then we'll look at the heap again. So hopefully that gives you some sort of concrete examples of how you'd use them. But one thing that you have to remember when you're using these data structures is a very important thing. That as a developer, you are able to accept a predictable level of inaccuracy. So inaccurate in so much that when you use this data structure, it might be wrong. And also, it might be wrong by some amount. But when you're using them, you accept the amount that you accept it to be wrong. And if you're okay with that, then you can use them. But another important thing to think about when you use these things, not just in a back-end system, but when you use them in something that's user-facing, is that the numbers that come out of these things might not be completely correct. So what does that mean to the business analysts who are using your software? What does it mean to the users if things are slightly wrong? Just something to think about. But without further ado, we're going to do 3 data structures today. The first one Bloom filters. So let's get started on this. They don't have anything to do with flowers at all. They're named after a mathematician called Burton Howard Bloom. And what they're used for is set membership tests. So you can test whether an element is in a set. And to begin with, the easiest way to explain why you would use them is to show a really naive example using Java. So we're going to use a Java util set here. And this isn't how you would code visitors to a site, because we're using strings for IPs and all that kind of thing, but it's just an example. What we're doing at the top is we're making a new set of strings. And hopefully you've all seen a set before in Java util. Then we're going to add 3 elements to this set, which are 3 different IP addresses. And then at the bottom there, we can call the contains method to see whether one of these elements is in that set. And the first element is, because we put it in there. And the second element isn't, because we didn't put it in there. Pretty straightforward. But the problem is, if you're using a set in order to do this kind of comparison of whether something's there or not, the set starts to get big because you're having to actually store the strings in the set when you're doing it. So I wrote a little program. I created random UUIDs, the 64-character unique identifiers in Java, and then I used Visual VM to have a look at the heap. And as we're moving up towards 1 million UUIDs in our set, we're looking at a fair amount of heap. It's 264 meg at that point. And if we were, for example, a very popular website and we were receiving millions and millions, maybe tens of millions of hits a day, if we were trying to keep this all in memory, it would suddenly get very, very large. So this is where Bloom filters come in. So yes, there's a paper at the bottom, which is called Space-Time Trade-Offs in Hash Coding with Allowable Errors. And you'll see that it was published a very, very long time ago when computers had significantly less memory than they do today. So it comes from 1970. I wasn't even alive. That paper's quite old. I wouldn't recommend reading it. There's better summaries, and hopefully this is one of them. And the best way to show you how it works is just by example. So we're going to initialize a new Bloom filter. There we go. Isn't that cool? It's just an array of bits, and it's of some size, and we'll talk about how you determine the size a bit later on. But it's an array of bits. They're all set to 0. That's the first bit. The second part is that we have some number of hash functions. And all of these hash functions have to be different, but I'm going to talk about how many you need later on. And then what we're going to do is we're going to add an element to our Bloom filter. So like in that example, the first element comes along, it goes through the first hash function, and it gets mapped to one of the bits in this array. And then that bit gets set to 1. And it also goes through the second hash function, which maps to a different bit, and that gets set to 1. Does that make sense so far? Nodding. Good. What we're going to do next is we're going to see if something that we didn't put in there is in the Bloom filter. So this element from the earlier example goes through the first hash function, and it goes to one of the bits which is set to 1. And then it goes through the second hash function, which doesn't map to any of the bits that have been set. And no matter how many hash functions you have, if any of the bits are not set, it's definitely not in there. When we check to see whether an element that we have put in there is there, it goes through those 2 hash functions like before, and it maps to the bits that have been set. And in this situation, the Bloom filter tells you maybe. So this is the probabilistic part, in that there's a percentage of error that may be occurring here. Before we look into what the percentage of error is and how it affects the Bloom filter, let's just show you how you can whack one of these in your code straight away. I would recommend using the Guava library, which is Google's sort of bag of Java tools that has loads of things in it. That was the latest version as of a couple of weeks ago. And then I've rewritten that naive example with a set, but using one of their Bloom filters. So you'll see at the top there, we've replaced our set with a Bloom filter, which takes strings. And it has a static create method, which takes 2 parameters. The first one is this curious thing called a funnel. All the funnel is you're telling the Bloom filter what object you are putting in there, and then Guava will go and do some hashing for you. There are built-in funnels for all of the primitive types, like integers and strings and so on. If you're going to be putting some of your own objects in there, then you can define your own funnel, and you say hash on this field and this field and this field. And the second parameter there is the number of elements that I'm expecting to put into the Bloom filter. So it's 10,000 in this particular situation. I mean, as you can see, that's actually wrong, because I'm only putting 3 in, so the Bloom filter would be too big. But just as an example. And then, like in the other set example, we just put those elements in the Bloom filter. And then instead of a contains method, like you get on a set, you get a may contain. In this case, the first one returns true, because we put it in there, and the second one returns false, because we didn't. Understandable? Excellent. So what does this do to our measurements? Well, as the number of UUIDs went up with the set, we obviously had to store every single string in the set. So we were getting on for 264 meg. When I was using the Guava Bloom filter, you can see that the amount of megabyte of heaps being used for this is very, very small. So even when I was expecting 1 million elements, we're only looking at 0.9 megabytes in order to do this equality test. So that saves a significant amount of space if you just want to do set membership. So you're able to suggest the size that the Bloom filter should be in the parameters, and we had 10,000 in the example. What this changes in the Bloom filter is the number of bits that you have in that array. So the number of bits goes up as the number of things that you want to store goes up. So if I wanted to store 10 things, it initialized with 40 bits. When it was given 1 million as a suggested input, it was 3.6 million bits in the Bloom filter, which is quite a lot. But bits aren't that expensive compared to storing the strings. By default in Guava, you get a 3% false positive probability rate. And I abbreviate this to FPP in some of the tables, if that, it's just a lot easier to put on the slides. And what that means is that when it tells you that something is there, there's a 3% chance that it actually isn't. And you have to think about whether that's okay. But with the Guava implementation, what's quite nice is it can take an additional third parameter, and you can specify the error rate that you're happy with. So if you think that 3% is too inaccurate, you can give it one. So in this case, it's 0.5% instead of 3%. And what this does when you change that is that as you change the false probability rate, the number of hash functions that the Bloom filter is using increases. So with my very accurate Bloom filter at the bottom, which is 0.0001% inaccuracy, there are 20 hash functions. So every time I insert and read something, it's being hashed 20 times either way. So those are the two design parameters, the number of bits for the size and the number of hash functions for the probability. And there you go, you understand Bloom filters. Wonderful. So what are they used in? Generally, caching stuff is a really useful use case. There's a paper that I've linked at the bottom there, which is from Akamai, which talk about using Bloom filters in order to, on high traffic websites, the first time that you visit, if you're like what they call a one-hit wonder, serve up a cached version of the page. If you are continuing to browse, so maybe you are an actual human interacting with the website, then using that Bloom filter, you can check whether they've been there before, and you can serve up some more compute-heavy content. The second one there is quite interesting. In HBase and Cassandra, Bloom filters are used to encode the locations of data so that when you scan across the cluster, it can skip out places where it knows that there is no data. And one thing that we used it for was in real-time matching. So people were able to search to specify a whole load of people on Twitter who they were interested in getting alerts for. Often these lists could be huge, like millions of Twitter authors. And then we serialized that into a Bloom filter into the database, and then we could poke it into our storm topology as a Bloom filter that we read out. So that's quite a nice technique as well, if you don't need to know who those people are. So great, 1 down, 2 to go. Next, we're going to look at count, min, sketch. This is a slightly more recent data structure, so it's not as old as 1970. And what it's used for, as the name suggests, is for tracking the counts. So if you're, for example, interested in reading a stream of data from Twitter and then storing the number of times that you've seen each hashtag, that kind of use case, then count, min, sketch is what you want to use. Let's look at the really naive example first using Java. So what I've used here, just to keep it concise, is a multiset. A multiset really is just a hash map in the background. It's a Guava thing. So the key of the hash map is the thing that we're tracking. So for example, the hashtag, and then the value is the counter of how many times we've seen it. So every time a hashtag would come along, it would get added and then incremented the counter. Does that make sense? Cool. So in this example, we use the IP addresses again, just to show. We create a multiset at the top, which is of string generic type, and then we add some things into it. The first 2 elements get added once, and then the last element there gets added twice. And then there's a count method that you can call to show you how many times you've seen it. That element at the top there we've seen twice, because we added it twice, and then the last element 0 times, because we didn't add it. Really simple stuff. But like the set example before, you'll also see that it starts to use a lot of heap when you're tracking lots of things. And the thing that's also annoying about the counting problem is that often if you're looking at streams of data like tweets, the tail of these things is huge. So the amount of things that have only been tweeted once is often very, very big. So I did the same thing as before. So I generated random UUIDs and the heap similar kind of profile. So as we got towards 1 million elements in our multiset, we're looking at 234 meg being stored, which is quite a lot. So if you're looking at, for example, the Twitter decahose, which is like 50 million tweets a day, and trying to keep this in memory, it starts to get really big, prohibitively big. And then you might want to spill it to a data store, but then you've got the time that it takes to do things with that and so on. Can you keep it in memory? You can with CountMin Sketch. So here's a paper which is quite recent. It's not the original paper. The original paper is from 2003, but this was a sort of summary paper that the original authors wrote, which is only a few pages long, and it describes it really concisely. And it's called CountMin Sketch because it does counting. Excellent. It uses the word min because you'll see that it uses a minimum function in order to find out what the count is. And it's a sketch because it's kind of an approximation. So what does it look like? I'll leave this here for just a few seconds. It looks like this. So remember that the Bloom filter was an array of bits, which we were using. The CountMin Sketch is an array of counters this time, so we want to be able to count things. So imagine that they're integers. But we don't only just have one row of counters, we have multiple rows. And when we talk about a CountMin sketch, we say that the width of the sketch is the number of counters that we have on every row. And then the depth of the sketch is the number of rows that we have. Each of these rows, if you look on the right-hand side, has a hash function that's associated with it. Now, it's important that every row has a different hash function. That's really important, and you'll see why in a minute. And it's best to show how it works by example, I think. So here's what we're going to do. We're going to add an element in, and I'm also going to shrink the sketch down so it fits on the slide. Let's add our first element. The element comes in, and then we go to the first row of counters, which has the first hash function associated with it, and we hash it, and it maps to one of those counters, and it gets incremented from 0 to 1. And then on the second row, we also run it through that different hash function, and it maps to one of the other counters, and it increments from 0 to 1. And then the same again on the third row. It comes in, it maps to the counter over there from the third hash function, and it increments from 0 to 1. Does that make sense? Cool. So then let's add the same element again for the second time. Each of these hash functions will map to exactly the same places, and it finds a 1 there. And then all of these 1s get incremented to 2. Cool. Let's add a different element in this time. So here's a new element. On the first row, it maps to that first counter, which was 0, and it increments it to 1. And then on the second row, what I've done here is I've simulated a hash collision taking place. So this element on the second row maps to exactly the same counter. This time, it can't increment from 0 to 1. It increments 2 to 3. So this is where it starts to get wrong. But that's okay, as you'll see in a minute. On the third row, it maps to a new counter, and it increments from 0 to 1. So now we want to query CountMin Sketch to say, how many times have I seen a certain thing? For the first thing that we've seen, which is the first element that we added, we run through the hash functions again, and then we get the values that are at those places. First hash function finds 2. The second hash function is where the collision took place, and it finds 3. The third hash function maps to 2. And then here's the min part of CountMin Sketch, is it takes the minimum of those values in order to give you a result. So the minimum of 2, 3, and 2 is 2, which is correct in this case. And then if we try and get the value out of the second element that we added, on the first row, it maps to a 1. The second row is where it collided, and it maps to a 3. And then on the third row, it maps to a 1. And then we take the minimum of those 3 values, and we get a 1. So you can see that by the hash functions being different, it means you will get collisions, but because you have lots of rows, hopefully, when you go over all of them, you'll get one of them that is accurate enough. So the thing that's different about the Bloom filter with CountMin Sketch is that for a human being with the Bloom filter, I think about how many things I'm going to put in there, and then I'm going to specify that amount, and then that's how it works. The CountMin Sketch is kind of different, because it initializes to a fixed size at the beginning, and it never changes. And the parameters that you use in order to size it are a bit more awkward to get your head around. And here's what they are. 2 parameters. The first one is called epsilon, which is useful. And this is the accepted amount of error that you are okay with being added to each item. So how wrong are you okay with the counts being? The second one is called delta, which is also really helpful. And this is the probability that when you receive a result, that it's outside of that epsilon value. So it's wronger than you are okay with. And those are your 2 parameters. And this code is taken from the library that I'm just about to show you. If you plug epsilon and delta into these two equations, then that calculates the width and the depth of the sketch. And we'll have a look at how that changes with the different values in a second. So you kind of understand it, which is good. Let's use it in some code. So I would recommend using the ClearSpring Analytics Stream library. This was written by the folks at AddThis, which I think do buttons on websites where you share stuff and then it counts how many times it's been shared. So I assume that they use this stuff quite a lot. And I've rewritten the example that we had earlier. So I've replaced the multiset with a count min sketch, and it's very easy. So you're declaring a count min sketch at the top, and it's taking 3 parameters in the constructor here. The first one is that epsilon value, which is how acceptably accurate should my counts be. So in this particular case, I want them to be 0.1% accurate. And then the second parameter, which is 0.99 there, is how much of the time should they be within the bounds that I specified. I know that's difficult to get your head around, but it makes sense after a while. And the third parameter there, which is, I wish they'd just overridden it, is a random seed. I've just put 1. And then you can add things into the sketch. I added those first 2 items once, and then I've added the third item twice. And then I can call estimate count instead of count. And it tells me 2 for the first one and 0 for the second one. So with direct comparison with the Bloom filter in the heap, it's kind of difficult to do because it doesn't scale with the number of things that go in there. But just to remind ourselves, when the multiset had 1 million elements in it, it was 234 megabytes of heap. If we have a look at what tuning the parameters does, at the top we've got a count min sketch that's fairly inaccurate. I'm accepting 10% difference in the counts that come out, but still 99% of the time it will be within that. And you'll see that as you tune it to be more and more accurate, with the epsilon and the delta increasing, the number of counters, the width on every row goes up, as you'd expect, but actually not up by that much. It goes from 7 to 17 counters per row. But where it gets quite big is the depth. So in the very accurate count min sketch at the bottom, there are 20,000 rows of counters, which obviously means 20,000 hashes being done. But the nice thing is that the heap usage is very small. So you can keep the counts of millions and millions of elements in about 2.7 megs of heap there if you want something fairly accurate. Or if you want something that's fairly inaccurate, you can get away with barely any heap at all, which is much nicer than using the multiset. And use cases for this, any kind of frequency tracking, counting stuff is the obvious thing. One really nice use case is NLP. So I read an example where they took a 90 gigabyte corpus of text, and then they funneled it all into a count min sketch to do the word frequencies, and that fit into about 8 gigabytes of data structure, which then means you can keep it in memory and do stuff with it, which is really cool. There's 2 extensions that I'm not going to talk about today because I will run out of time, but there's an extension called Heavy Hitters, which uses a heap next to the count min sketch in order to keep the top X of things that you've seen. So the obvious use case there is, what are the top hashtags right now in my area? And there's also an extension called Range Query, which you'll probably have heard of in Solar and Lucene, and I'll leave that as an exercise for you to read about. So good, we're 2 things down. Is everyone still awake and alive? Good. The last one, the more complicated one. I'll apologize up front for having skimmed over some of the maths in this one, but I hope that you'll thank me for it. It's also the one with the silliest name, hyperloglog. Who's heard of hyperloglog? Most of the room. So hopefully I'll get this right. The easiest way to understand it, what you tend to do is you go and download the paper, and then you open up the paper, and then you look at all that crazy maths, and then you get very scared, and then you put it away, and you go and do something else. So what I'm going to show you is sort of the journey that the authors take towards getting towards hyperloglog. So what is it for to begin with? It's for cardinality estimation. So given some huge list of items, what's the cardinality? So how many unique items are there? So we're going to start off as per the other ones with our naive Java example. And for this, I'm just going to reuse the set, because the mathematical property of a set is that each item is unique. So what I'm going to do is create a new hash set. I'm going to stick some things in there. There's 3 unique elements there because we add one thing 3 times. We call size, which is effectively the cardinality, and it says 3. You all know how sets work. Hopefully that makes sense. But just to remind you as before, when we're using large amounts of things in that set, when we get up to 1 million elements, we're looking at hundreds of megabytes of heap being used. And if you're, for example, computing the daily visitors of a top website like LinkedIn or Google or something, you can see that doing this cardinality stuff in memory is actually quite a challenge because you have to hang on to all of it while you're doing it. So what we're going to do now is a very gentle walk into hyperloglog. So it's an iteration of an iteration of an iteration of different techniques. If you see the progression, it's, I think, easier to get an intuition as to how it works. The actual implementation is still quite complicated, but I'm hoping that it will have some kind of impact by going through it today. We're going to start off with something called linear counting. So this is from a paper in 1990, and it's called a linear time probabilistic counting algorithm for database applications. The application that they're talking about here is, if I have a massive database table, how do I know how big it is without having to actually scan everything? They use this technique that looks a little bit like a Bloom filter. So here we have an array of bits. We had an array of bits in our Bloom filter. It's of some particular size. We're going to call it size m. Then what we're going to do is have one hash function, just one, and we're going to insert an element. We run it through our hash function, and it maps to one of the bits, and it sets it to 1. And then we're going to add another element, and it's going to map to one of the bits, and we're going to set it to 1. And then what we're going to do is an equation, and I'll explain what this equation is. So the variables in this equation, m is the width of our linear counter. That means how many bits do we have. And then w is the weight of our mask, which is just the number of ones that we have. And then ln is the natural logarithm. So if you plug in this, you get minus 10 times the natural logarithm of 10 minus 2 divided by 10, which is 2.2 as an estimation of the cardinality. The cardinality is 2, so it's not far off. However, the variance on this is really, really big, and it gets quite unwieldy at large amounts. But there's an intuition there that you can record something and then do an equation in order to estimate. So next we're going to move on to log. And this is much more powerful, but it's much more complicated. And we're going to look at the multiple steps that we use to get there. First off, we're going to have an intuition of flipping coins. So everyone's flipped a coin before. 50% chance that you get a head, 50% chance that you get a tail. Now, if I got 5 heads in a row, how many times do you think I flipped the coin? Maybe 20? Something like that? If I got 100 heads in a row, how many times would I have been flipping coins for? Thousands? If I got 10,000 heads in a row, I've probably been flipping the coin for a very, very, very long time. The idea is the more things you get in a row, the less likely it is that it would have happened and the longer I would have been doing that particular thing. So with that intuition in mind of rows of heads, let's use hashing. So let's take an element, let's hash it, and then get the binary representation, and then let's count the number of zeros that it begins with. This particular binary representation starts with a 1, so we have no leading zeros whatsoever, so we record a 0. Second one, let's hash it, same hash function, and then record the number of leading zeros, which is, in this case, 1, because it starts with 1, 0. And then another element and so on, and record the number of leading zeros. Now, what if we could use that intuition that it's more rare to get lots of leading zeros in a row and plug that into an equation? Well, we could do something really, really naive, like 2 to the power of the maximum number of leading zeros that we had to estimate. So 2 to the power of maximum number of leading zeros, which is 1. So 2 to the 1 is 2, and our cardinality estimate is 2. But that's wrong, because it's 3. But this is just another step towards getting to where we're going. So the authors then show how you can take that intuition and you can improve it. And one way that you can improve it is to do lots and lots and lots of different hashes. I'm talking like many, many, many different hashes. And then you can take the average of all the recordings that you've seen in order to give you something that's slightly more accurate. But the problem is as you throw all these hashes at it, it starts to get really expensive and a bit clunky. So is there something more clever that you can do? And the authors show that there is, and there's this thing called stochastic averaging, which I'm not going to go into the maths, but I'll give you an intuition. What you can do is you can get away with just using one hash function. On the right-hand side, you declare a number of buckets. And this is very similar to count, min, sketch. They're just an array of counters. And those counters are where you're going to store the number of leading zeros that you've seen. And what you do is when you hash it once, you snip off the prefix of the hash, and I've just used 4 as an example. It's different in the real thing, though. And that prefix maps to one of the buckets. And then the remaining part of the hash, you count the leading zeros. And then in that bucket, if the number of leading zeros that you have is greater than or equal to the one that's already in there, you record it. I hope that makes sense. But you take the first bit, maps to a bucket, record the leading zeros to the last bit, and then you have a fixed number of counters that you're using. And then the authors do something even more magic, which is they show that, given that, you do 2, and you raise it to the power of the sum of the maximum zeros that you've seen divided by the number of buckets that you have, which is fixed, multiplied by the number of buckets, multiplied by a magic number. And if you ever see an implementation of this, you'll see a massive array of magic numbers. And what these are some statistical analysis that they do to show that at different sizes of estimates, if you multiply it by a magic number, it nudges the estimate in the right direction. Wonderful. But I'm not going to show you the magic numbers. But from all of this stuff, they show that they can get an average error in the cardinality estimate of 1.3 divided by the square root of the number of buckets. And they also say that with 1,024 buckets, you have enough counters to do estimates of billions of elements, which means that you get a 4% cardinality inaccuracy. But the nice thing is, with 1,024 buckets, you only need 5 bits per bucket in order to do this, which means that you can do hyperloglog in about 5K of memory, which is absolutely nothing. But actually, that's not the whole thing. So there's the hyperloglog paper, which improves it even further. And what the authors do now, and it's called near optimal in this case, is that when they get the counts of the leading zeros, they throw away the largest 30% of recordings that they have, and they leave the remaining 70%. And just by doing that, because the sketch always tends to err on the large side, they can get their error down to this now, which is 1.05 divided by the square root of buckets. So if we plug in 1,024 buckets, we get 3.2% inaccuracy. And then they can't even stop there. They go one step further, and they say instead of doing a regular average in the power of 2, they do a harmonic mean instead, which is a slightly different way of calculating an average, and it goes down to 3%. So that's an intuition of how it works. It's quite magic, but it's also very cool. And if you're really good at math, you'll really enjoy the paper. If you want to use it in your own code, you don't have to do any of that stuff. There is the same library that we used before for CountMin Sketch, has hyperloglog in it, ClearSpring Analytics Stream. I've rewritten the example from earlier. We create a new hyperloglog at the top. We give it the percentage of accuracy that we're interested in. We add some elements in, and then we call cardinality. And there you go. Heap size, brilliant. So if we're doing that cardinality estimate with a set, hundreds of megs of heap. If we're using hyperloglog, nothing. So if you can imagine, if you had lots of these in a storm topology, you're not going to be putting any pressure on your workers at all. Use cases for that: constant time cardinality estimate, for example, unique site visitors, estimates of massive tables, because you can either do 2 things. You can either have a running hyperloglog counter that you keep all the time, and you keep adding to it, or you could just use it when you, say, do a big batch job and you stream out loads of data and you just count on the fly. And there you go. That is it. So we've gone through 3 probabilistic data structures. I hope they made sense. And we've also had a look at some code before and after to show you that there's libraries out there that make it really easy to use this stuff. I almost choked at the beginning, which is excellent. Thank you very much for listening. Just to recap, Bloom filters are for set membership, good for caching. CountMin Sketch, really good for counting how many times you've seen something. And hyperloglog is an interesting story, and it's really good for cardinality estimates. And that is it. Thank you very much for listening.
Okay. Thank you. Thank you, James. Can we unmute this mic? Can we? One. Oh, okay. Wake up. Thank you, James. You started 2 minutes ahead of time and finished 2 minutes ahead of time to give 2 more minutes for Q&A. Any questions in the room?
This is where I get really scared.
Regarding the Bloom filters, have you compared the performance and memory consumption with the cuckoo filters, for example? Because they have their own advantages.
Sorry, can you say that once more?
Cuckoo filters.
Yes.
Because the main problem of the Bloom filters, you could not remove the data from it. Cuckoo filters allow.
Wait, that's the really tricky thing. So the particular use case that we used it for, it was absolutely fine not to have that data in memory because we didn't need to iterate through it later. But obviously, if you do need to iterate through it later, then that's the trade-off that you have. So I don't know, maybe, for example, you could have a Bloom filter but then store the data in a Solar Elasticsearch index for lookup when you need to. But yeah, it's use case specific. I hope that answers your question. Maybe it didn't.
Yeah, okay. Basically, there are some tasks when you need to remove the data from the cache, for example. You have the cleanup and etc.
So that's a really, really important point. So not only can you not get the data out, as in if you had a set, you could remove the data again. When you put stuff into a Bloom filter, it's very, very difficult to remove it, if not impossible. So there are extensions to Bloom filters that can do these things, but having looked at some of the papers, it all just gets really complicated. So you do have to think that if you are keeping a load of Bloom filters in memory of particular data sets, what happens when that data set changes? So say if you have a cache that invalidates, then you have to reload the whole Bloom filter again. And that's definitely something to bear in mind. Thank you for bringing that up. But I haven't got any good advice there.
Okay. Next tricky question.
It's not so much a question as that I just wanted an intuition that might be clear to everyone, but has always helped me. Bloom filters, I think, are different from a lot of probabilistic algorithms in that one of the two questions, the no question, is always right. So you can add or use Bloom filters in a lot of situations where if you get an answer yes, you do a lookup anyway, but if you get an answer no, then you save a lot of work, and you can do it without any probabilistic trade-offs.
Yeah, that's a really, really good point, and I should have said that in the talk. So if you were using a Bloom filter as part of a loading cache or something, then that's really good because you have 100% guaranteed correct no. So yes, if that filters out most of your requests, and then when you do get a yes, you do something else, then that's a really good use of it, yeah. Thanks for bringing that up.
I have a question related to hyperlog in a MapReduce environment. Is there any chance to do calculations in each mapper or each reducer and combine them afterwards? So especially for unique user calculations where I don't want to sort first by user?
That's a really good question, and I don't know the answer. I know that, for example, with Bloom filters, you can do operations to kind of combine them, but I'm not sure if the same is true with hyperloglog. Maybe somebody else may know the answer. I guess if you do lots of separate hyperloglogs and then combine them, it just gets more and more and more inaccurate. But I don't know, sorry.
Any more questions or comments? Just please raise your hand. One.
I wanted to answer the previous question. The Clay Springs have an article on how to combine hyperloglogs with different, even if they have different accuracy.
Okay, great, cool. I'll have a look at that. Thank you.
Anyone else? Going once.
At the front.
Twice.
So you can increase accuracy of the algorithms by adding more hash functions. Does this have a notable an impact on the runtime, or does it not matter?
So the hash functions don't need to be really complicated. They don't need to be like cryptographic level hashes or anything. They use a technique which I think is called pairwise hashing, where you actually just have one hash function, but it's parameterized. So for example, in the count-min sketch, some of the inputs to the hash function would be the row that you're on, and then it can do some like modulo arithmetic. So as far as I know, as long as they're all constant time, it should be okay. But I can't give you any good proof.
Okay, thanks.
Okay. Any other hand I don't see?
I think that's it.
Okay, thanks, James.
Cheers.
Thanks, everyone.